Okay, maybe we can start the meet now while waiting for the others to join. Okay, let me introduce findeme.com first. So Findeme is a community-based learning where we host some events like this, and we also contribute to open source projects. We have also weekly meeting to express your ideas and create something together. Okay, without further ado, let's start this session. Please welcome Aditya Putra Santosa.
Okay, let me share my screen then. Okay, but have the recording started? Not on. Okay, so let's start. So yeah, thank you to Fedemi for hosting this event. So today I would like to talk about the introduction to scalable system on how to create it or how to apply this to any kind of backend system that you have. A little bit introduction about me. So my name is Aditya Putra Santosa. You can call me either Aditya or Adit. So right now I work as a senior software engineer at Sendit. I graduated from ITB back in 2020, and then I already worked in Sendit during that time until today. Yes, so our agenda today is that I want to talk about what is a scalable system, and then we also would like to see how we can approach on making this your system more scalable, and then some kind of pattern that people usually use to do this. Oh yeah, feel free to unmute your mic or raise hand or just put any question in the chat, and I will immediately answer it. So let's start with the definition first. So this is scalable system. So usually when people talk about scalable system, they usually mean about this part, the performance scaling. So what this means is that how does the system handle growing input? Like, does it handle it well? Can it handle 10,000 user, 1 million user, as well as it handle 10 user or one user? And to measure this thing objectively, usually we measure the response time, we measure the throughput, we measure the latency, and then this thing is important because it ensures a fast and reliable user experience. Now, other than performance scaling, there's also another metric. I remember there's a couple more, but usually we only focus on these three things. So the other one is maintainability scaling. This one is more of like a question of how, as the team grow or as the system grow, how easy is it to add the new feature, or how easy is it to fix the bug, or if we want to replace a certain component or on our system, we want to know like how easy is it to do it. And we measure this by measuring the development speed. We also measure, like, for example, the time spent on bug fixing or the toil spent by the engineer while using that system. And this maintainability, it's important because it's crucial for long-term development speed. But because from my experience, it's kind of useless if you have a speed or a reliable server, but it's not really maintainable. And then the last but not least is cost scaling. So this one is usually the most important one for the business people. We want to know, as the traffic increase, how does the cost affect it? Like, does it explode uncontrollably, or does it grow in a predictable or an efficient way? If you have a proper scalable system, then the cost should like grow linearly, or it should help us to manage the budget efficiently. Now let's talk about how people do scaling. So the first one is vertical scaling. This is the traditional way of doing scaling, and we do it by increasing the server power. It's basically just as simple as if you have a server with two CPU in it, two core CPU in it, and then it got bottleneck on the CPU power, you basically just need to buy a better CPU with more core in, for example. Or if you got a bottleneck on your RAM, then you add more RAM in it. Or if, for example, you host an AI application and then your GPU cannot handle the model, you buy a better GPU. So this is vertical scaling. It is very simple because it's basically just buy a better or more advanced hardware for our server, but there's also cons for this. So the first one is that it has a hard limit, and eventually after you upgrade several times, you will eventually get like to the latest, most powerful hardware you get on the market. And then if you still got bottleneck at that point, then there's nothing we can do other than waiting for a newer or better hardware. Other than that, it's also a single point of failure. Since we only have one big server, if something happened to it, then all of the system or app will crash down, basically. Now, the more modern approach to scaling is by doing what we call horizontal scaling. So instead of just having one big, more powerful server, we copy it and have like a clone of it, multiple of it. So for example, from before we have one, now we have 8 more server. And then we also distribute the work across all of the server. So the pros here is that there's theoretically no limit to this. For example, if one of your server can already handle 100 user, and then you want to handle 10 times that or 100 times that, then in theory, you just need to multiply the number of server by 10 or by 100. And also because the system is distributed, it's more resilient compared to having a single server. So if one of them goes down, like this one, it goes down, then the other 8 can still pick up the work and your system will still go normally. But then the cons of using this is that it's very complex because instead of having one single big app, you have to deal with distributed system and all of it full, basically. Now let's take a look at how people usually do horizontal scaling. So one of most popular pattern for that is by doing microservice. Before that, let's take a look at a more traditional way people build their app. So what we have here is what we call a monolith app, where everyone contribute to the same app and same code base here. So we have order team, they contribute to the order service inside this app repository. Now this work well when when the number of developer is not that big, but then as the number of people grow, we start to get more issue. So for example here, since everything is in one place, if one of the service fail, for example user service, they push a code that causes nil pointer exception or null pointer exception, and it causes the app, then it will also affect payment. So people cannot log in, and then people also cannot create any payment. They also cannot create any order and other. And then another failure here is that if we got a heavy load on one service, since the resource are shared between all service here, right? So it uses the same CPU, it uses the same database. If one of them cause a heavy load on the resource, then it will also affect the other service. So if we receive a lot of order, then maybe it might cause the user to not be able to do login, or they cannot pay, for example. And then yeah, that's two part that affect the user experience. Now another cons that affect the internal people or the developer is that because this whole thing is deployed as one big app, the release schedule will also depend on all the people involved on this app. So for example, if payment team they have some change that they want to deploy, but they don't want to deploy today, they want to deploy it next week, for example. And then order team, they also have a change that they want to deploy, but they need to deploy it in about 1 hour. This will cause a conflict because, well, so either payment team need to revert their change or they will need to resolve it between those two. Yeah, this will become complicated with them. And then other than that, as shown before on the horizontal scaling example, since we basically just clone the app to another server, if we scale this at the same time, all service will also get scaled. So if we receive a lot of order and then we copy this server multiple times, well, we can handle a lot of order, but we also indirectly scale the payment service and user service, which might not be really necessary for us, and this will cause unnecessary costs for us. So yeah. So how do we solve this? Usually, when the number of team get bigger and bigger, they will start to see the domain get separated more. Like this one, we see this one handle only order domain, this one handle only payment domain, this one only handle user-related domain, At that point, they can do something called microservice. So they take a large single application or what we call monolith before, and then we break it down into a collection of small independent service. So each team will have their own application and they will also have their own database. They can technically share their database, but usually it will have their own smaller database for each service. And because it's also spirited, they can also have their own release schedule. By doing this, when one service fail, the other will still work. So if, like on our example before, user service, they push a bad code and cause nil pointer exception and crash the service, it won't affect any order creation or any payment creation at all. Also because the resource is different, so if we have a heavy load on order service, it won't affect the other service. And because the release schedule is also independent, if payment service, like example before they want to release next week and order service they want to release it now, they can just do it because it doesn't really affect the other team. And because it's also spirited, we can only scale service that need heavy traffic. So if we suddenly see a lot of spike to our order service, we only need to scale this one particular service and doesn't need to scale the other one. So this will also make the cost better for us. Now this microservice, it works best for large organization with multiple teams mentioned here. Oh, and then also another pros to this approach is that each service can be developed using the best language for their use case or team. This actually happened for me during my time at Sendit. So at first we start with JavaScript. So every service is created using JavaScript. But then as more TypeScript people joining in, we can split the service. So the newer service they start using TypeScript, and then later on when we realize that we need a better service with better concurrency handling, so we create a new service with Golang in it. So that's another advantage of microservice. Compare that with the large service before. Technically, you can use multiple language in one app, but it gets complicated quickly, especially if the features start to get bigger and bigger. No, a microservice is not really a silver bullet. So there are some pitfall for this. Is this? So the first one is that instead of having just a simple application that you can develop easily, it become a complex distributed system. And since it's distributed, you also need to handle things like distributed tracing, monitoring, logging, and then there's also an issue with network communication. So let's take a look at our big app example. Let's say here that order service, they want to call create payment. Like previously, this is so simple. We basically just need to call this function here on the code. So just create payment, call it, and then it will do create a payment. But now since since the service is on its own service, it need to be done on, for example, API call. So payment service, they need to provide a post/payment API, and another service will need to call that API. So yeah, and then because of that, it is also subject to things like timeout, network inconsistency, and then latency, stuff like that. And then because the database is also distributed, there is also a risk of data consistency. So for example, if you want to do for every successful payment, the order need to be successful. Because it's separated, there might be an edge case where the payment is successful, but then order still gets stuck in pending or stuff like that. And then because it's also using API based, there's also an issue with security. So from before, previously everything is internal. So if you need to call a function, you just need to call it directly. But now it's an API, everyone technically can call it. So you need to introduce things like API key or IP whitelisting to make the service more secure. And then the largest pitfall in microservice is what I would call nano service. So this is an example of nano service. Nano service is what happened when we break down microservice to form. This is actually a real life example that happened on my team before on Sendit. So payment service, back then we divided into smaller ones. So we have e-wallet service, we have credit card service, we have virtual account service. It's owned by its own team. And then at the time, we also break down e-wallet service more. So we want to integrate with OVO, we want to integrate with Dana, Link Aja, PayPal, Apple Pay, for example. and then we end up creating a new service for each one of them. So we have OVO connector just to handle any call to OVO. We have Dana connector to handle any call to Dana. Now this is actually not bad if you have enough people on your team. So if the team is big enough, then nano service might be good. But then what we realized at that time is that we only have around 5, 10 people, and then we have to manage around a lot of service, and then this become a hassle when we do maintenance in it. For example, one of the biggest one back then is we need to migrate from TypeScript 3 to TypeScript 4. Usually it's automatic, but there are some library that have different behavior, so we need to change it for every single one of our service. And yeah, you can imagine the effort that we need to spend on doing that. Also, because of this thing, it's so nano or it's so small, there might be a lot of code duplication here. Like this OVO connector and Dano connector, they both technically only do the same thing. We basically just need to map and then call the API and then map the response again. So there's a lot of code duplication, and if we need to change logic in one of them, we also need to change logic in all of them. Otherwise, we will get a bug here. So yeah, that's one of the pitfall of, I would say the biggest pitfall of microservice. That's about microservice. And then now let's talk about how to scale the communication layer. So previously I mentioned that usually on microservice we do it by API call like this. Right? So order service, it will call payment service via API call. For example, this one is a post/payment API. Now this is subject to network issue, things like timeout, network latency, and then there's also an issue where because there's a synchronous API call, order creation is blocked until payment request return something. And then if you are also not properly handling the error, if something happened during payment creation, it will also cause an issue on the caller. So it will also cause an issue on create order. Um, a better way, I would say a better way to do this is to use event driven. So instead of doing API call, we publish an event. So for example, here order service, after it create the order, it will publish an order created event to a message broker. This thing can be anything that can handle message. So it can be Kafka, it can be SQS, it can be RabbitMQ, or it can also be your in-house message broker. Now, instead of order service calling payment service, this time the responsibility is reversed. So payment service will consume that order created event, and then every time it see, oh, I see a new order is created, payment service will be responsible to create the payment. So this thing is done asynchronously. And because it's done asynchronously, order can still be created even the payment is not yet created, which might be good or not depending on your business use case. And also, if there's any error on payment creation, it won't affect order creation. Payment service can just retry consuming the message if it got any error. Okay, so maybe payment creation might not be the best thing for this because it's usually pretty fast. But this kind of process, it works best for a process that require long waiting time. For example, if you need to do a report generation, you need to generate a report for past 1 year data. So you need to pull all data, you need to aggregate data, you need to calculate the summary and stuff like that. Instead of doing a one long blocking API call, you can just do it asynchronously like this. And then, oh god, there's also a pitfall for event driven. So I would say the major one is that it's hard to debug. So instead of a simple API call, A call B, B call C, C call D, now it become a chain of event. So A publish event, and then somewhere on the log we need to find a log that say, oh, this service it consumed this event and then it do something. So it's not, from my experience, it's not really easy to debug this, especially locally also. And then there's also another pitfall. Because we depend on this message broker here, it might become a single point of failure. So if Kafka goes down or if SQS goes down, then well, all of our system will goes down. Anywhere, any system that use this event driven will also goes down. But this can be mitigated, which I will explain, I think at the last of the session about failure handling. And then the last one is that because this whole thing is asynchronous, we also need to acknowledge that the data update is not instant. So let's go to our first example. So when we create a payment, it will immediately create a payment here, and maybe it will also update something on the order DB. So this whole thing, because it's synchronous, everything is instant, right? But now because it's asynchronous, it might be not instant. For example, if there are a lot of message here, we have like 100,000 message backup in the queue, then if we publish a new message, then it will need to wait until those 100 messages are processed first. So it might not be instant for this. Okay, that's about if scaling the communication layer. And we also have a way to scale the database. So these are two, I would say, most common way people do database scaling. The first one is by doing read-write replica. So this one is very useful if your application have a lot more read than write. For example, you have e-commerce application. Usually people will they will scroll and then see a lot of product first before buying something. The act of seeing product, we can treat of it like a get something or a read something, and then at the end of the day, they will just do one write or one payment to that. So yeah, the ratio of read to write is skew heavier to the read, and for a thing like that, we can do read write replica. So basically, you just need to create a read-only copy of our database, and all read-related queries, so all select-related query will go to this DB, and then this DB can also be optimized to be more read optimized. I remember AWS have some option like that. And then there's a more complex way to do database scaling, and that is by doing sharding. So sharding is when we split the data into multiple database. For example, here we have two database. The first one, it only handle order from user A to M, and the second one, it only handle order from user N to C. This one we can maybe do it for something like tier-based customer. So more VIP customer, they will use a better database so they can get better response time or stuff like that. But this thing is more complex, so you need to be really careful if you want to use this. But anyway, other than these two things, there's actually one better way to scale your database, and that is by doing caching. So you can treat the cache as a simple high-speed in-memory data store, for example, Redis. And the idea here is that we store frequently accessed data, for example, like the user profile or the user setting or the top 10 best-selling product. So we don't need to read it every time from the DB. So write will still go to the DB, and then the first time we read from the DB, we still do it from DB, and then but we also store it to our cache here, which is Redis. And then the next time we need to read, we just read it directly from our cache. That's about database scaling. And then now I'd like to talk about handling failure. So as mentioned before, because we do microservice, our service is subject to things like timeout. They're also subject to other service failing. And the most simplest way we can do that, we can handle this kind of failure is by doing retry. As an example here, other service, the first time it called payment service, it got 500 error. So we retried again, still got 500 error, and then we tried again until we got 200 okay. Now retry is simple, but there are some couple of way that we need to be careful with this, and one of them is we need to use. It's better to use exponential backoff for this, where we need to wait a few seconds exponentially. So the first retry we wait 2 seconds, second retry we wait 2 times 2 4 seconds, third retry we wait 4 times 2 8 seconds, and so on and so forth. Now why we do this exponential backoff? It's because of the thing called retry storm. The retry storm is what happens if you have a lot of requests that need to be retried at the same time. Let's go an example. So imagine you have 100 requests per second on order service, and let's say that all of them fail. So on the first second, you got 100 requests, all of them fail. On the second, you get another 100 new requests, and then you also need to retry that 100 requests from before. So you need to send 200 requests. And then on the third second, let's say that the second time it failed. So on the third second, you get another new 100 requests, and then you need to retry those 200 requests before. So now it becomes 300 requests, and well, you can see how this goes. So at like 10 seconds, we already have 1,000 requests that need to be retried. Yeah, this can technically with exponential backup retry storm can still happen, but it's to help slow it down a bit. Oh, and then we also need to make sure that its request is idempotent or safe to retry if we want to use this approach. Otherwise, it will might cause some unwanted side effect that we have. Now, if let's say, for example, if you already use exponential backup and then you still got retry storm, there's another way to handle that, and that is by using circuit breaker. So this circuit breaker, it's behave exactly the same as what electrical circuit breaker we have on our house. So in real life, so what it does is that on usual day, if there is no issue, then the circuit breaker will let the request go through. It won't. It will just let the request pass. So at that time, it is at its closed state, similar to how switch work in electricity. If it's closed, then it will let the electricity pass through. Now, if we see any failure on the request, we will see like how many times does it fail? Is it still under threshold? So let's say our threshold is 2. So on the first failure, 1 is still below 2. So it's still close. And now we get another timeout. And then because it reached the threshold, the circuit breaker will go through open state. And now because it go to open state, anytime there's a call to the request, it won't let the request pass through. It will just return error for this. So we won't burden the supplier here, the supplier service here, with a lot of requests in case of failure like this. And then we can also introduce something called reset timeout. So let's say reset timeout is 10 seconds. So after 10 seconds, the circuit breaker will go through half open state. And then when it go to half open state, it will let some requests pass through. So we can think of it like an experimentation. So it will let maybe 3 requests pass through, and then it will analyze those 3 requests. Does it fail or is it successful? If those 3 requests are still failed, then it will go back to open state again, and then it will still block all of the requests. But if those 2 requests are successful, then maybe the issue is already resolved, and then it can go back to the closed state again, and it will let the connection pass through. So this is one of the way we can handle failure in microservice circuit breaker. Now, earlier I mentioned about event-driven. So the message broker here. So earlier I mentioned that if the message broker goes down, then it might become a huge single point of failure because everything will goes down. And there's a way to mitigate that, and that's it by doing what we call message outbox. Message outbox in a very simplest term is you just basically, instead of order service directly publishing to message broker, it write the message or the action first to a table. We call it outbox table. And then you will have another service here. It could be a service, it could be a cron, it could be something else, but we call it message relay, and this will be the one that is responsible to publishing to the message broker. So on normal scenario, order service, it want to publish something, it will insert to the table first. Message relay, it will read from the table, oh, there's a new message that need to be published. It will publish those messages to the broker. Now let's see what happens if the broker fail. So this part here, it will fail. Order service will still publish the message. It will still insert new message to the table. So it will still keep inserting new row, new row, new row. And order service will not notice any failure here. So it will still behave normally as usual. And then message relay will retry all of those messages. So it will read the first one, publish, oh, it failed. It won't do any updates. So then next time, for example, 5 seconds later, it retry again, and so on and so forth until the message broker is up again. So this is how we can handle failure in message outbox, in event driven by using message outbox. And yeah, that's it for how to make scalable system. Any question?
I think I have one question to ask.
Yes.
When should our app use monolith or microservice? Thank you.
That's a good question. So microservice and monolith, like I will say that microservice is better used when you have a large organization. So I think you can also think of it like if your organization have large enough people that it can be separated into its own domain. So like example here we have three team which only handle their own domains. Payment team it only handle payment stuff. Then I will think at that point it will be good to split it into microservice. But if your team is still small, so for example, you only have a couple of people, 10 people, and some people still work on multiple service together. Like these people still work on order service, but sometimes it also work on payment service. Then monolith might be better at that time. Actually, like the largest company in the world, like I remember Google and Facebook, they still use monolith up until a certain point, and then they start to transition to microservice.
Okay, I think I have one last question to ask.
Okay, go.
This is out of the context, but I want to ask how can we prevent our code from being stolen from others? Like in this case, like if we have team.
Article from being stolen. Hmm. Okay, so I will say that it's almost impossible to prevent your code from being stolen. Um, but I think like from what I see, like from most business, what really matter? Okay, maybe the most important secret algorithm that one can be stolen technically, and it's if it might be bad if it gets stolen, but most of the time, like 90% of the code, even if it got stolen, it's how do I say this? Yeah, it might not really matter. Lah, is what I will think. Yeah, if your business fail because of the code got stolen, then you might need to reevaluate the business, think of it again. Unless this code is like a super secret algorithm. For example, you are Instagram, and so Instagram have their own secret algorithm, right, which make them addicting, for example, or TikTok, something like that. So those things, their code or their algorithm is the main one, and yeah, that thing need to be guarded. And if it fail, then if it got stolen, then the business might fail. So for that kind of stuff, how can we prevent it from getting stolen? From what I see, like there are two way people do this. The first one is to well, the simplest one is to restrict access at all. So we only let a couple of people know about this secret or your main core service code. And then the second way people prevent it from being stolen is, but I forget what I want to say earlier. Oh wait, there's another way. So the second way is to do code obfuscation. If you have heard of it, let me type it out. You can do obfuscation. This would usually, I believe, this is what usually large company use on their own app. So if you can also try it yourself. Like if you go to any big company and then you go to their page source, it will just be a random like gibberish, right? So that's one way we can kind of protect our system, but it's not really 100% reliable. If someone technically can still reverse engineer it and get your original code from that. What other way we can protect code from being stolen? No, I think it's only the
I
two.
would say we can use the microservice approach where not only like one people can have the entire code, but instead people divided by and some microservices, so they only have that code only.
Yeah, that could also work. So you could technically split your main like code logic into multiple smaller service, so there's no one people that I believe that's also what like big company like KFC or like the food and business company do. They don't put one secret recipe on one place. Instead, they distribute it onto multiple company. But yeah, it's still subject to the thing that I mentioned before. Technically, people can still gather all the data and reverse engineer it. But yeah, it can help slow down the stolen part. There's a question from Budi. So for DB scaling, is there any weakness for cache? If there is, and the update when you must. That's a good question. So that is one. I would say it's one of the two hardest thing to do in caching, and that is cache invalidation. Cache invalidation is that we need to know like when we need to invalidate or remove the data inside the cache. For example, as you mentioned there, if we have any data update, do we need to immediately remove the data from the cache, or we just need to wait until it expires? So the answer to that is that it honestly it highly depend on the use case scenario. I can say one example for this. So in Sendit, we use caching to store the setting or the credential of our client, and this client can be updated. But when we update it, we don't immediately remove the caching because one, it's pretty hard to remove it from all of the cache. Well, and yeah, this is because we use microservice, so there's a lot of service that read from this cache, so it become hard to reset this. But for some case, it might be better to remove or yeah, remove it directly from the cache. And this can be done by using a distributed caching system like this example here is Redis. So every service that you have will read from this one distributed cache. So if you have something like this and you really need the latest most updated data, then yes, you will need to remove the old data from the cache. And then for the second part of the question about the automatic update, from what I experienced, that can be handled two way. So the first way is that we put it on the service itself. So after there's a write to the DB, it will also do an update to the cache. And then the second way people do that is by using something called change data capture or CDC. So after it write to the DB there will be a service that handle. Oh, there's an update on the DB. So that one will be responsible to update the data on Redis. So that's one way to do it automatically using CDC. Oh wait, I forgot to mention about the weakness of cache technique. Yeah, there's weakness to caching. One of them, like I would say the biggest one is it costs. This thing is super expensive if you compare it to normal DB. So people usually will only cache the most important part and like only smart part of their data. They won't cache everything or every data that they have. Other than costs, other than cost, and then they also cache invalidation. If you do distributed caching, there's also an issue with doing the key naming. So you need to put a key name for your cache, and sometimes it's straightforward, but oftentimes it's also quite hard to determine which name to use for your key. And if you use the wrong name, then it might cause a conflict with other purpose. So yeah, this also have happened on before when I was working at Sendit. So we have two different flow that use the same cache key, and because it update the cache with different item, well, the sometimes the service will fail, and we don't really know why until we take a look. Oh, turns out it's using the same cache key, so it update the wrong data. So that's one weakness to. Yeah, that's several weakness to caching. Yep, no problem.
Okay, before it ends, I have one more question to ask
Yep. Go on, go on. Please go on.
about the event driven, the Kafka. So, where does
Mhm.
the data stored after the consumer consumes the data? Is it deleted by the Kafka or how?
So that okay, that one depend entirely on which message broker you use. So if you use something like SQS or RabbitMQ, then yes, it's deleted after. I believe. Okay, I might be wrong, but if I remember correctly, the behavior is that after the message is consumed, you cannot reconsume it again unless it's published to the queue again. But that's different with Kafka because Kafka, I remember it have a persistent storage for the message. So after the message got published, so like for example here, order created, it got published to Kafka, and then it got consumed by payment service. The message is actually not deleted. It's stored on the, I forget, is it a DB or a log file somewhere on Kafka? So technically, if you have another service, user service, it want to consume from Kafka, there are two options there. It can consume from the latest message, so it won't see the previous order created event, or it can consume from the first event. So yeah, because it can consume from the first event, the previous message that is already consumed, it can be reconsumed again by another service. So that's how Kafka work. So yeah, this that kind of thing, it entirely depend on which message broker you use.
Okay, I think that's all for this meeting. Do you guys have any last question before the meeting ends?
Mhm.
How about Budi? Do you have any question? Oh, I think no, yeah. Okay, I think that's all for today. Thank you guys for joining this meeting. I hope you guys can learn something from this. Thank you, especially for Aditya Putra Santosa. Thank you for being a speaker in this session.
Okay, thank you also to Fademi for hosting this. If you have any question, can reach out to me on LinkedIn or on any social media. That's it. Thank you.
Okay, that's all for now. Thank you guys for joining. You may leave now. Thank you.